did. Yeah, I had a little something special. I titled my project "Boat versus Wind." Mine was basically testing how wind affects the velocity of a sailboat, where there's boats can sail against the wind. Just a brief history background. Sailing is thought to have began around 5,000 years ago, somewhere in that range, when Phoenicians and Egyptians started sailing underneath cloth sails on single logs, or sometimes they'd build rafts out of multiple logs that they used as long, narrow boats. About 1,000 years later, that would have been about 3,000 BC, I believe, square sails started to become common on boats, kind of like the bottom right picture there. Then around 500 BC, moving forward further in time, the Phoenicians started building ships with two big masts. And then in 900 AD, the triangle in Latin, which is from the French word Latin meaning Latin, those sails were adopted. And then between 15 and 1650, sailmakers started using flax fiber to make their sails. My project statement was, can a sailing boat go in the direction opposite to the direction of the wind? And that was a very interesting question to try to solve. Of course, obviously the answer is no. A sailboat can't sail directly into the wind at 180 degrees. The wind would simply blow it backwards in the reverse direction and cause the boat to lose ground, as demonstrated down in this picture. As you can see in the pink range down here in this picture, there's no sailing possible from one side to the other. And if sailors needed to travel in the opposite direction of the wind to get to where they were going, they did it one of two ways. They could either steer the boat in a zigzag pattern back and forth into the wind, different directions, which is called tacking, or they could they'd go off in one direction, tangent to the wind, make a loop, and when they were backwards, when they were facing away from the wind, it would kind of give them a boost, kind of a push, and they'd use that to come back and take it at the other angle, and that's called wearing. And you can see both of those down here in this example. And then they'd repeat the process. They're basically the same thing. It's just wearing is basically making a figure eight instead of a wave pattern, but they both have the same general idea. Some of the factors I considered, of course, people have done this.
What's the second word?
Wearing.
Wavering?
Wearing.
Okay.
Okay. Some of the factors I considered, and of course people have done this further in detail, who've really studied this, have probably considered a lot greater and more important factors than what I did, but just some of the factors I considered were the wind speed, since wind doesn't always blow at a constant speed, of course, it changes with the weather. And in my experiment, I set the true wind velocity equal to 30 miles an hour. I set it as a constant, and the apparent wind velocity constant at 50 miles an hour. And of course, those aren't always realistic, but those are just a couple numbers I used to solve for some of my variables. The location, the Great Lakes won't have the same wind velocity as what they will in the Atlantic Ocean. Winds change based on your location. And weather, as rain, that'll hinder the wind's performance on a sail, and rain will make the sails heavier, which will make it'll make it harder for the wind to blow, and it'll cause you to lose velocity. Some of the two calculations I used were, this first one I solved for A. A is the apparent wind velocity, W is the true wind velocity, and V is the velocity of the boat, and then alpha is the true pointing angle of the wind. And that is A equals the square root of W squared plus V squared plus 2WV times cosine A, or cosine alpha. I didn't really use this equation much since I was solving for beta, which is down here on this second equation. And I set A as a constant, but this kind of goes along with the equation I did use. So if you did need to solve for A, that's how one would do it. The equation I really used was I solved for beta, which is the sail angle. That equation is beta equals arc cosine of W times cosine alpha plus V divided by A. And then true wind versus the apparent wind. I know they sound like they're the same thing. I know it doesn't sound like there's much of a difference. But basically, true wind is just the wind itself. It's whatever the wind's doing, whatever it's blowing, whatever direction, however fast it's blowing. It's just is the wind. The apparent wind is whatever the wind effect is on the boat in that specific place at that specific time. because it's not going to be the same for a sailboat 50 miles ahead. It's going to be headed in a different direction,
The same
have a
thing
different
as
speed.
relative wind, you know.
Right, yes.
Kind of generic word you'd use under circumstances would be wind relative to, I mean, the absolute wind and relative to the ship.
Right.
Because it's moving.
Right.
Okay.
Yeah, I just named it apparent wind. And then,
Yeah, well, so you're saying that's the terminology they use in the
right.
in the field.
Right, and then BV, of course, is just the velocity of the boat, and this is basically your basic Pythagorean theorem. If the boat velocity is 15 and the true wind is 20 miles an hour, then your apparent wind, the effect the wind's having on the boat, is going to be 25 miles an hour. It's your basic Pythagorean theorem. I'll come back to that in a bit. That's where I switched over to my experiment, or the Excel chart. Okay. Oh, sure. Sorry. Does it need to be any more?
More. Still can see it. Okay.
Okay. It cuts off the graph, so I'll just scroll down a little bit in a second. What I did basically, I was trying to solve for beta again. I set the W, which is the true wind velocity, alpha, which is the true pointing angle, and the A, which is the apparent wind velocity. I set them all constant. Of course, these numbers aren't always going to be realistic, but I just used a couple numbers just to try to show the correlation. And then I set the V velocity, I set it to an equal, to where it was increasing 2 miles an hour every interval. From 3 to 37, and then I calculated beta based on this data using the two equations down here, just like what I just showed you. And oddly enough, I found that, as the graph shows, I found that as the wind angle increases, the boat velocity decreases. And I know that sounds funny. That may sound odd, since I know it sounds like if the sail was further out, the boat would go faster. But I believe in my I got a live demonstration on a website I found, and that'll demonstrate what I'm explaining here. But I believe.
So the graph is so the x-axis is the sail angle relative to the boat,
Right.
right?
Right.
And then
Right. And the other axis is the boat velocity in miles an hour.
okay, so it's the x-axis is degrees, the one as you plot it, and so as you increase it, the velocity
Decreases.
So what's the zero angle is perpendicular sort of to the boat.
Right.
Like this.
Right.
So this is zero. Okay, and then you start moving it, and you are so then what? So but the wind is. What is the relation between the wind and the? I mean, the setup, like this, the setup is the, the boat relative to the, so this is the boat, sail versus the boat. What about the boat versus the wind? What is the angle? Is it so it's constant, but what is it? Or not? Is it
I set the wind equal to constant, at a constant 30 miles an hour, and then the
no,
apparent at
the
50.
direction. What's the angle?
I didn't use the wind angle. I left that constant at 65. That's what the true pointing angle is. That's the wind angle, the way that the angle the wind's hitting the boat.
In your presentation, there was a picture, right? And so your particular picture was the true wind was perpendicular to the boat. That's just the picture, but you certainly you can have different angles. And
Right.
So that you're considering a particular situation when you were moving exactly perpendicular to the true wind, or is it just, or do I understand it correctly?
Yes.
Okay, so just you pick an example and to specific situation,
Right.
and just to make it
Right. And I got, like I said, my
compute it. Okay, so then and then you end with zero. Okay, so this is the boat, this is the wind. So when it seems like when your sail is straight, you should have zero.
Right, it is. I just didn't start with, because I started the velocity at 3 instead of 0.
No, I didn't mean the speed. I meant the angle of the sail. If it is So if you were dealing with that picture that you showed, then the 0 degree is 90 degrees between the boat and the sail. Is this so? This is the boat.
Right.
This is the sail.
Right.
That is the 0. But then if the wind blows this way, you should have 0 velocity. And when you start turning, you start to increase the velocity.
I think this the way this reflected was.
Maybe you did the opposite. Are you sure this is the 0?
Yes.
Maybe this is the 0.
Yes. I think the way this looks the way it is because I believe, and I'll show you in my live video here in a second, I believe this is because the boat is sailing against the wind, not with it. This is what it would look like if the boat was sailing at an angle against the wind instead of with it. And I'll show you what I'm talking about here in just one second. Let me pull this website up. There it is. Okay, let me adjust it here real quick first.
Okay.
Okay, as you can see, the sail's expanded pretty much as far out as I can get it to go. The wind won't let it go out any further. And as you can see, the boat
Right,
is...
so right now the speed is 0, is it?
Right.
Oh, because it just slides off.
Right, and then as I move the sail inward, the boat starts moving. I agree, it's not very fast, I know, but that...
Why is it moving forward? Oh, why is it forward or backwards?
It's moving forwards. It's just slow. But this isn't...
Yeah, that's the weird...
let me
it
try.
is moving forward because...
There we go, let me try different...
It's because of the rudder. The rudder only allows motion in a certain
Right.
direction.
Right.
So the keel is... Or the... Well, I don't know the terminology, but as long as it catches anything, that push is transferred by the shape of the boat, and motion can be transferred to forward motion.
Let me try a bit of a different angle here. I didn't take the rudder into consideration. I mean, I did, but I didn't really use the...
It is considered. Are you rotating the boat, or is the boat rotating under the wind? Or
I am, but I just set it to a straight equal line. What I was trying to show was how the wind...
right. So the direction of the boat versus the direction of the wind is fixed, and you can change
Right.
it, but it's not unaffected by the wind. So
Right.
the wind doesn't push it aside because the ship is designed in such a way that it would not turn because of the wind.
Right.
Unless it turns the
Right.
whatever the thing is. So it's in control of its direction.
Right. And then I
And
guess...
so in this particular case, it hits, as long as it hits the back of the wind, it moves forward, right?
Right.
Even no matter how small the angle is. So which we just saw.
Right. And then I move back out. As you can see, it stops. It comes back to 0 speed. You can pull it back in. It's moving forward again. And I know it looks slow compared to some of my data, but this is just a basic representation. Some of their data isn't realistic since they didn't take like the all they measure is the wind speed and the wind direction and the boat speed. They don't have the actual sail angle measured down here, as you guys can see. So you can tell it's not perfectly accurate, but it does represent the point that I was showing in the graph in my Excel chart.
Yeah, so your picture, remember that you mentioned the Pythagorean theorem, that is the key to everything.
Right. Yes.
The how you get the piece of the force that is whatever the part of the force that the wind that goes along the sail is lost, and the perpendicular one is what actually produces the forward push.
Right. And then just some of the references I use where I got some of my information. It's kind of like my bibliography page. And that was about all I had.
All right. Questions, please?
Do you know what a knot is?
Knots, that's basically how they measure their speed in sailing terminology. I think it was equal to 1.15 miles an hour, something like that, yeah, when I looked it up.
They used to measure it with knots, I think.
Right.
The speed.
Oh, before they had miles?
Yeah.
did they throw like a rope with knots on it in outside and see how far it stretches backwards? Depending on the speed, the farther the speed, the more knots on the rope you see. That's where it came from, apparently.
That's neat.
Can you show hacking versus
Sure.
versus wearing?
Yes.
Yes. Okay. So any ideas of which advantage one over the other?
I would say probably wearing would be the advantage, since you're getting, like I said, you're getting a velocity boost whenever it comes around the tip of that 8 shape, whereas tacking you're not, you're just going back and forth into the wind. But the thing about wearing is it would take longer while you're making that loop back around, so they both have their advantage and disadvantage.
It seems that, so the wind, because in either case, I can't exactly see the nose of the ship. So the nose of the ship on the left, the tacking one is always forward, sort of, more or less.
Right.
And then, which means that at some point, at those maximum points, sort of, you have the wind is blowing straight at you.
Right.
So at that moment, your sail has to be
It is.
parallel.
Right, and it's at the top and the bottom
So
of
you
the...
have to be very active with that, and
Right.
and it seems to me that maybe the second one you don't have to do as much, because whenever you're facing the wind, you're moving backwards.
Right, right.
So even though you probably don't want to, you still want to have flat wind, so you wouldn't go too far back. But at least
Right.
there's no so much pressure on the mast or something, because you don't have this nasty moment when you were moving forward and while being pushed back, which
Right.
is what tacking produces.
Right.
And those tangents. So that's the calculus language that we want to use. Is the hardest part is when the wind is when you were the wind is tangent to your path.
Right.
Okay, so otherwise, so you just keep going, so the second one.